end Chapter 5 with 5.7. This has to do with applying everything that we've learned in Chapter 5 now. One of the main things was to be able to determine minimums and maximums of a function. And so what 5.7 is now going to be doing is it's going to have you minimizing and maximizing functions. For example, if you're looking at the area of a certain fenced-in area, you're going to want to maximize that area given a certain amount of fencing that you have. So the idea is you're going to be applying all of these calculus skills now to, at times, creating some sort of function. Sometimes the book will give you an equation that would express, for example, area, but sometimes you're going to be actually creating the functions and then solving where are the minimums and maximums. I am going to set out a warning. As far as the skills that we have, this chapter is nothing new. All we're doing is trying to find the minimums and maximums of a certain function. The challenge of this all is going to be to set up the functions. When you're not given the function that you want to minimize or maximize, you're going to be responsible for setting it up yourself. And this is going to be challenging. What I hope that you will do is just take the time to be frustrated. If you need to, walk off the frustration and come back to it to get a fresh start. Move on to another problem. Do what it takes because some of these will be difficult. In this section, what you're going to be finding is that I'm really only going to be working through examples. Since there is no new lesson, I'm just going to be stepping you through some homework problems. There are 2 vocabulary words that I am going to use freely as I go through these examples, so I do expect you to know these. Primary equations are going to be the equations that you use to maximize or minimize a situation. So this is the function that you're actually going to be deriving. That's the primary equation. That's the one that you want to minimize or maximize. The secondary equation is just going to be an equation that may be needed in order to help you write the primary equation, so that it is in terms of one variable. You'll see what I mean as I go through these. So here we go. We're going to start right into it. Example number 3, what that states in your book is to find 2 positive numbers that satisfy the given requirements. The first thing that I want you to recognize is that we have the product. It's going to be 192, and the sum is what we're trying to minimize. So I'm going to go ahead. We're trying to find 2 positive numbers. So I'm just going to go ahead and say we have x and y. These stand for our 2 positive numbers. And they could be anything, but I do know that x times y is equal to 192. And I also know that x plus y is going to equal to, I don't really know what it's going to be, but I am going to represent it by s because it has to be some sort of sum. So we're going to take these to the next slide, but I just want to kind of demonstrate what's going on here. Alright, so your textbook outlines some steps that you may or may not want to use. I did them a little bit differently than your textbook, but what I always suggest is to draw pictures if you can. And for this particular problem, you can't really draw pictures, but what I would like to do is just kind of restate what we did on that first page. So if I could, I just want to show you what's going on. I could pick any number for x. Let's say that I chose and guessed, well, if I pick the number 2, that's a positive number, and then I'm going to solve for my y to see what that would have to be, so that the product was 192. What I'm going to get is that y is equal to 96. So in that case, what we could go ahead and see is that x plus that y then would be equal to 2 plus 96, and that would get us 98. Alright, so I'm not really sure that sum seems fairly small, but is it a minimum? So let's plug in another value. Let's try x equals 3. Alright, so I'm going to have to go ahead and solve for what y would have to be in order for our product to be 192. Y is equal to 64 when I divide both sides by 3. So let's see, we're getting a bit smaller here. Alright, so we get 67. So you can kind of see it would take a lot of guess and checking before you would actually come across the 2 numbers that you could multiply to be 192 and then add to be some sort of number. So what x and y value is going to get us a minimum sum? So this is kind of just, this is not really a picture, but it is kind of showing you what's going on. And don't be like this guy over here, don't give up like him. The first thing I'm going to do is write my primary equation as a single variable. So I've already written the two equations. My primary, that's the one that I'm actually trying to minimize. That would be my sum equation. So I'm going to write that here, x plus y. Alright, and my secondary, the idea is if I were to try to derive this function that I'm calling s, I'm going to call it my s function because it's a sum machine. It's giving me some sort of sum based off of these two inputs. The idea is if I try to derive this, I would have these two variables, so I couldn't derive with respect to one variable. So what I'm going to do is I'm going to use my secondary equation that they provided, x times y. This is kind of like a specification that we need to follow through with. And I'm going to go ahead and rewrite this in terms of x. So I'm going to solve for my y, and what I'm going to get there is y is equal to 192 over x. Okay. Using my secondary equation, what I've done is I've rewritten y in terms of x. So what I can do is sub that in to my original equation. So my primary equation that I'm trying to derive is going to be s is equal to x plus 192 over x. Alright, so I've transferred my equation that I found in step 3 that's in terms of one variable, and it says determine a feasible domain of the primary equation. Well, when you're looking at this, our input is x, and remember we want our x values to be positive. So my domain that I'm going to specify, I'm going to just write it like this, is going to be, it could be 0. Oh, I'm sorry, I'm going to not include 0 because it has to be positive. Positive is not, that's not, 0 is not positive. So to infinity, anything within that range is okay for me. Okay. So finally what I'm going to do is I'm going to determine the desired minimum and maximum values by our calculus techniques. So I'm going to take this is a function in terms of x now. I'm going to rewrite this just because I'm lazy, and I'm going to try to figure out the fastest way for me to derive. I'm going to rewrite this as x to the negative 1. And I am going to find the derivative because I would like to find out what are my critical values. Where am I going to get the peaks and valleys? So when I do derive this, I'm going to get 1 and then plus 192 is just some sort of scalar multiple, so I am going to go ahead and just ignore that but derive this piece, x to the negative 2. Alright, so what I get is, so now I want to figure out, alright, when is my derivative going to be equal to 0? So I'm going to solve for that. I am going to rewrite this like that. And then I'm going to multiply x squared to both sides and divide both sides by -1. What I'm going to get is x squared is equal to 192. And then when I solve for this, I'm going to get equals, and in your calculator it's going to be plus minus 13.8. But now do remember that we do want our x variable to be something positive, so I'm going to cancel out this negative. All I'm interested in is the critical point x equals 13.8. So now I'm going to ask myself, oh, what is y equal to? Well, don't forget, and I'm going to flashback. Flashback, y was equal to this 192 over x. Oops, I messed that up. But y equals 192 over x. So now I simply can solve for my y. Y would be equal to 192 divided by 13.8. 13.91. Alright, so these right here are going to be our minimum values that will get us our minimum sum. X would have to be around 13.8, y is going to be about 13.91, and what you would get is the smallest sum possible. Alright, so we're going to also do number 9 as an example, and what it asks us for is to find the length and width of a rectangle that has the given area and the minimum and a minimum perimeter. So we're trying to, I guess, use as little bit of outside material to build this rectangle. The first thing that I want to point out is the thing that we are actually trying to do, or the thing that we are trying to do is minimize. And what are we trying to do? The perimeter. Okay, so I'm going to say perim. And equation that will be helpful, an area equation may be helpful to us. There are two things that they give us, so I mean there's probably useful information in that in the area that they gave us. Alright, so to get more space here, I'm going to first start by drawing a picture, just so I can kind of visualize what's going on. And here is a rectangle, of course, and they are going to be asking us for width and length of this rectangle, and the area that they do want us to have is 64 feet squared. So the thing that I'm going to start to do now is, as part of the second step, I'm going to set up my primary equation in terms of one variable. So the primary, once again, is the one that I'm trying to either minimize or maximize. And so what we did say is that's going to be our perimeter. And what I'm going to do now is come up with an equation that will give me the perimeter. Well, if you look over here, the perimeter is going to just be two lengths. So a length plus W plus L plus W, that would be the perimeter. So I'm going to go ahead and say, well, two lengths plus two W's, or two widths, is going to be what gives me my perimeter. But once again, if I were to try to derive this P function right now, this perimeter function, what's going to happen is I'm going to run into issues, because what am I going to drive it with respect to? Am I going to drive it with respect to L or W? So we want to get it into in terms of one variable. So I am going to need my secondary equation here, and they did give us area, and so area of a rectangle would just be given by length times width is equal to area, which we know is 64. So now it doesn't really matter, but I'm going to be writing this, I'm going to be solving for one of these variables so that I can write the perimeter in terms of 1. So I'm going to go ahead and solve for length in terms of W, so just divide by W from both sides, because now what I can go ahead and do is say that perimeter, can take this, sub it in for my L, and what I'll get is perimeter is equal to, which is equal to 128 over W plus 2W. So step 3, when we're looking at this, I do have my perimeter, and when I'm looking at W, I need to determine what is the domain, what are all possible inputs that I could put in here. And once again, I'm going to specify that this has to be positive. It has to be a rectangle, so I'm not going to include 0. If it included 0, then you wouldn't have a width, and we do need a width for a rectangle to occur. But really, you could go as far as you wanted. Alright, so as long as it's from a positive number, I think that's going to be a feasible domain for this thing. So now, finally, I'm going to go ahead and derive this. I'm going to derive, I have written P in terms of, W, and I'm going to start deriving. One thing I am going to do is rewrite this as 128 W to the negative 1 plus 2W. So what I am going to get is negative 128. This is a lot like the other one that we just did, so I'm going to breeze through this. I need to find my critical values. Once again, same type of thing. I'm going to multiply both sides by W to the second, but then divide both sides by negative 2. So these cancel each other out, those cancel each other out. What I get is W to the second equals, and then 64. So then when I go ahead and square root this, I'm going to get W is equal to plus negative 8. So what you will find is I don't need the negative. W is equal to 8. So the best width, in order to get a minimum perimeter, what we found is this critical value right here of 8. And you can go back and solve for your now, right here. And you can go solve for here. This is going to give us our length, and what you'll find is it's just going to be 8. So it turns out that if you have a rectangle, the best thing for you to do that will cause you to have the least amount of materials to build, for example, this fence, would be if you had an 8 by 8, so a squared in area. So here we have it. Oops. Stay tuned for some more complex examples.